This is Classical Physics 2, and we're in Chapter 20, Working Problems. And the first problem we'll look at will be number 4. We'll get warmed up on number 4. And it'd be nice if I was in the right chapter, looking at the right problems, but can't have everything. Chapter 4. A 4-cylinder gasoline engine has some efficiency. Boy, that doesn't look much like an efficiency thing, does it? That looks better. Efficiency of 0.22. And delivers 180 joules per cycle. The engine fires 25 cycles per second. 25 cycles per second. Determine the work done per second. All right, so A. Work is what? Work is force times distance. Work is what are we trying to calculate anyway? Determine the work done per second. Okay, so work per second. All right, so I've got 180 joules per cycle times 4-cycle engine, 4 cylinders, times 25 cycles per second, S. In cylinders. Cylinders and cycles have the same abbreviation. Anyway, so we end up with 1.8 times 10 to the 4th joules per second, which is going to be the work done per second. Now, why wouldn't we multiply it by efficiency anyway? Oh, because that's not the amount of gas I'm using. The gas I'm using is going to be, to take that number divided by 0.22. Okay, so that answers that question. So B, what is the total heat input per second? Total heat input per second. Well, the efficiency is going to be the work divided by QH, which implies that the heat input will be the work divided by efficiency. And we want work per second. So the QH per second is going to be 1.8 times 10 to the 4th joules per second divided by 0.22. Which is going to be 8.2 times 10 to the 5th joules per second. So that's what I'm going to have to, the heat I'm going to have to put in 8.2 joules times 10 to the 5th joules per second in order to get the amount of work out that I'm getting out. I see. If the energy content of gasoline is 130 megajoules per gallon, how long will 1 gallon last? All right, so I got 130 megajoules per gallon, and I'm going to divide that by 8.2 times 10 to the fifth joules per second. And I'm going to end up with 158.9 seconds per gallon. And I only have 1 gallon, right? 1 gallon lasts. So I'm going to have 1,589 seconds. And I don't have that many significant digits, so I'll change that to 26 minutes. So 1 gallon is going to last 26 minutes. And with 2 significant digits, that's about as best as I can do. All right, problem number 10. A heat cycle exhausts heat at 340 degrees centigrade and has a carrot efficiency of 38%. What exhaust temperature would enable it to achieve a 40? So we want a new efficiency of 45%. All right, well, there's E1, there's E2. So E1 is equal to 1 minus temperature low divided by temperature hot. Now the temperature hot isn't changing, it's only the temperature low that is changing. Where's 50? Exhaust heat at 340. What exhaust temperature? Okay, so we're gonna keep low 1. Okay, so the hot temperature, which isn't going to change, temperature low 1, 1 minus E1, and when I change my numbers to Kelvin, I end up with temperature hot is 340 plus 273, so I can get to Kelvin, divided by 1 minus 0.38, and I end up with 989 degrees Kelvin. Okay, well so that's my T hot. And then I want to know my efficiency 2 is going to be 1 minus the temperature low 2 divided by the T hot, which I already calculated, and I want that to be 45%, 0.45. Okay, so 1 minus temperature low 2, exhaust temperature 2, is going to be I don't think so. Okay, so temperature exhaust 2. I put the 1 on the other side of the equation, which makes it negative. I make both the negatives positive. I got 0.55 temperature hot. Okay, that's what we're going to do. 0.55 times the temperature hot, which is 989. All right, so I've got, we'll call it 544K. And then I'm going to subtract 273 to change it to degrees centigrade. So temperature exhaust 2 would have to be 270 degrees centigrade in order to have the efficiency that I want to have. All right. Number 18. The working substance of a certain Carrot engine is 1 mole of an ideal monoatomic gas. During the isothermal expansion portion of the engine cycle, the volume of the gas doubles. Okay, so I got 1 mole and volume 1, volume 2. Volume 2 is equal to 2 volume 1. Okay, it doubles. While during the adiabatic expansion of the volume decreases by a factor of 5.7. Okay, so decreases by a factor of 5.7. I guess I should draw a picture. Maybe. Hard to say. Alright, so volume 3 increases 5.7 volume 2. Alright. The work output of the engine, work 920 joules per cycle. Compute the temperatures of the 2 reservoirs between which the engine operates. Good thing this is just a mere level 2 problem, otherwise it might be difficult. Okay, so what do we know? So from section 20-3 on page 534. All right, from there we find that QH is equal to nRT hot natural log volume B divided by volume A, which is in this case is going to be nRT hot natural log of 2 because I doubled my volume. Alright. Since this is a Carrot cycle, we know that E is equal to 1 minus T cold over T hot, which is also equal to work over QH. We know that that's the case. So from that, we can calculate that work is equal to QH, T hot minus TL over TH. Okay, or that's going to be, seeing that we know what TH is, that's going to be nRTH natural log 2 T hot minus T cold divided by T hot. Alright, and then from that we can derive that this is going to be equal to N R TH minus TL natural log 2. So right here I can go boom, boom, and then I get that. Okay, so that's good. Now we're going to look at figure 20-7. Alright, so I'm looking at figure 20-7. Alright. Alright. And we see that between points B and C, which is the abiotic relationship, the ideal gas law are used to express the temperature ratio in terms of the volumetric ratios. Okay, so P, B, V, B raised to the alpha is equal to P, C, B, C raised to the alpha, which implies that N, R, TH over VB, VB to the alpha, is going to be equal to N, R, T, C over VC, VC raised to the alpha, which further implies that TH is going to be TL, V at point C, V at B, raised to the alpha minus 1, which is going to be TL 5.7 to the 2/3. Yeah, to the 2/3, because we know alpha is 5/3. We calculated that before. So the work is going to be NR TH minus TC TL, TH minus TL, natural log 2, which ends up being NR TL 5.7 to the 2/3. I got a parentheses in the way. 2/3 minus 1 times natural log 2. And we can rearrange that to say TL is equal to W, work, divided by NR natural log 2, 5.7 raised to the 2/3 minus 1. Alright, so now I know I can put in all my values, because I know that work was 920 joules, and I've got 1 mole, and I've got 8.314 joules per mole Kelvin. And I've got a natural log 2, and I've got a 5.7 to the 2/3 minus 1. Okay, so I find my low temperature to be 73 Kelvin. That is pretty low. And then I find my temperature high to be that 73 Kelvin times 5.7 to the 2/3, which ends up being 233 Kelvin. That seems a little low. So carrot engine, monatomic gas. Well, must be true. Read it in the paper, didn't you? All right. Number 26. Luckily, these are even problems that I'm working, and therefore you can't look in the back of the book to know whether or not I got it right. But I've got it on pretty good authority that I did. Number 24. An ideal Carrot engine has an efficiency of 0.38. If it were possible to run it backwards as a heat pump, what would the performance be? Right. So for a efficiency is work divided by QH, and we know 4-4. The coefficient of performance is going to be the same. So the coefficient of performance is 1 over the efficiency, which comes out with 2.6. So if I could run it, if I had a Carrot engine with an efficiency of 38%, and I could run it backwards, then I would end up with a 2.6. Okay, well, after that problem, number 30. A central heat pump operating as an air conditioner draws 33,000 BTUs per hour from a building and operates between the temperatures of 24 degrees and 38 degrees. If the coefficient of performance is 0.2, that of a Carrot air conditioner, what is the efficient coefficient of performance? Okay. So for an ideal gas, equation 20-4-4C. TL divided by TH minus TC. And so my coefficient of performance effective 0.2 times TL over TH minus TC, TL minus, whatever it is. I got to change things to Kelvin. Okay, so I'm going to have 0.2273 plus 24 divided by 14. K on the top, K on the bottom, which goes away. And I end up with 4.2. Okay, part B, 30 part B. What is the power in kilowatts required of the compressor motor? Okay, so part B, I'm using equation 20.4a, coefficient of performance QL divided by W, which implies that my work, QL divided by coefficient of performance, the effective one, And work divided by time would be watts. Joules divided by time is watts. So that's going to be QL divided by time divided by the coefficient of performance, the effective one, 33,000 BTUs per hour. I'm going to divide by 4.2. 10,055 joules per BTU. 1 hour per 3,000 seconds. 1 kilowatt per 1,000 watts. Well, I certainly did mess up that, didn't I? Anyway, so I put it in my calculator, and I get approximately 2.3 kilowatts is what it's going to take to do that. And then the C part of the question is how many horsepower. So the C part, so I got 300 kilowatts, and I have 1 horsepower per 746 watts. I get that from the front of the book in case anybody was thinking about looking. And I get 3.1 horsepower. Yeah, if I look in the front cover of my book, I have a conversion of watts into horsepower. Yep, sitting right there under power. All right. But I'm sure you found that out before. Okay, well, you are doing 38 next. We have a 2.8 kilogram piece of aluminum at 43 degrees centigrade. It's placed in 1 kilogram of water, 1 kilogram of water, in a styrofoam container at room temperature, 20 degrees centigrade. Estimate the net change in entropy of the system. Net change in entropy. Okay. So the issue is the change in entropy is going to be the change in entropy of the aluminum plus the change in entropy of the water. So we have 2 things to calculate. Okay. First thing we want to know is the final temperature. So that's the first thing we're going to have to calculate. All right. So in the mass of the aluminum, specific heat of the aluminum times the delta T is going to be the mass of the water times the specific heat of the water times the delta T of the water. Okay, so that's what we're going to need to do first. We can leave everything in degrees centigrade. That's perfectly okay. So we got mass, aluminum, specific heat, aluminum, temperature initial of the aluminum minus temperature final is equal to mass of the water, specific heat of the water, final temperature minus the initial temperature of the water. Alright, well, that being the case, I can find the temperature final is going to be mass of the aluminum, specific heat of the aluminum, temperature initial of the aluminum, plus mass of the water, specific heat of the water, initial temperature of the water, divided by mass of the aluminum, specific heat of the aluminum, plus the mass of the water, specific heat of the water. Well, I think it's time to put in numbers. Final temperature. So the final temperature, what do we have? 2.8 kilograms? Yes. All right, so 2.8 kilograms, 900 joules per kilogram degree centigrade, 43 degrees centigrade, plus 1 kilogram, 4186 joules per kilogram centigrade degree, 20 degrees, divided by 2.8 kilograms, 900 joules kilogram centigrade degrees, plus 1 kilogram, 4186 joules per kilogram centigrade degree. Okay, now for that. Temperature final equals 28.64 degrees Celsius. All right. So that is just so wonderful that I got that already. So now I know the temperature final of the mix. Now I'm looking for the change in entropy, and I'm looking for the change of entropy of the aluminum guy plus the change of entropy of the water in order to get the number that I'm looking for. Okay, so I look at the change in entropy of the aluminum guy. Integral. I go from my temperature of the aluminum, which was 43 degrees. So 43 degrees to my final 28.64. Change in the Q of the aluminum divided by the temperature. Okay, and dt. And then right, so that's going to be mass of the aluminum, which is a constant, specific heat of the aluminum, which is also a constant, integral, and I'm going to have to change my, I'm sorry, but I'm going to have to change my temperatures to Kelvin at this point. 43 plus 273. Okay, I'm going to go 316, 273 plus 28.64, 301.6. 301.6 dt over t. Okay, so I'm going to have mass of the aluminum specific heat of the aluminum, and I'm going to have natural log of T evaluated at 316 and at 301.6. I'm going to have mass of the aluminum, specific heat of the aluminum, natural log of 301.6 divided by 316. Alright. And then, when I get done there, I'm going to have to still find the change in entropy of the water. Well, I don't really have to do all the math over again. Mass of the water, specific heat of the water, natural log, and the final temperature is 301.6, so it's going to go on the bottom, 301.6. And the guy that goes on the top is going to be 28.6 plus 273. 301.6 goes on top. 301.6, and the guy on the bottom is 293. 293. Okay, so that's what those two guys are. Alright, so now I've got to go and find, I have to add them together. Alright, so I got 2.8 kilograms, 900 joules per kilogram degree centigrade, natural log, 301.6 over 316 plus 1 kilogram, 4186 joules per kilogram degree centigrade, natural log 301.6293. And when I get done putting all that in my calculator, I get it 4.4 joules per K. So that's going to be my change in entropy. And let's hope they put a problem like that on the test, because that'll assume that we have to use more paper to get to the right answer. All right, looking at problem number 50. Specific heat for a mole of potassium at low temperature is given by C sub V is alpha T plus B. Why did we do alpha? Well, that's an A. That's not an alpha. That's good. Trying to figure out why they did Greek alphabet and not Greek alphabet. AT plus BT cubed. Okay. Where A is 2.08 millijoules per mole Kelvin squared. And B is 2.57 millijoules per mole Kelvin to the fourth. Determine by integration the entropy change of 0.515 moles of potassium when the temperature is lowered from, okay, so I'm going to go 3.0 K, and I'm going to go down to 1 K, and we have moles of potassium 0.15 moles. Okay, there we go. Okay, well, we've got the problem written down. Okay, well, first thing we'll look at is change in Q is number of moles C sub V dt. All right, so we got that guy, and we know that the entropy 50. Doing 50? Okay, change in entropy, that's what I thought. So the change in entropy, integral T1 to T2 of dq over T. All right, so we've got integral T1, T2, number of moles, CV dt. Alright, that looks nice. Number of moles can go on the outside. Integral T1, T2. And we have alpha, not alpha, A plus BT cubed dt, d capital T. All right, that's all right. And then something's not right. Something isn't right. Okay. All right. This is T squared. A T squared, because I had AT plus BT to the third, and I'm dividing that by T, so that's why those things come out. All right, so I've got N, I've got AT plus BT cubed over 3, evaluated at T1, T2. Okay, now I can put numbers in. 0.15 moles, 2.08 moles, that's millijoules per mole Kelvin squared times 1 Kelvin minus 3 Kelvin plus 1/3 2.57 millijoules per mole Kelvin to the 4th times 1 degree Kelvin cubed minus 3 degree Kelvin cubed, close parentheses. I put it in my calculator and I get the change in entropy is minus 4.0 millijoules per K. Okay, last problem in this problem set, 52. A general theorem states that the amount of energy that becomes unavailable to do useful work in any process is equal to the temperature low times the change in entropy, where temperature low is the lowest temperature available, and the change of entropy is the total change in entropy during the process. Show that this is valid in the specific case of. a falling rock that hits the ground. Okay, falling rock that hits the ground. A. All right, so the change in entropy would be the change in Q over T. The ground, let's say, kinetic energy of the rod hitting the ground okay, so the change in temperature of the ground is going to be 0. I'm not going to change the temperature at all. Okay, so the change in entropy is going to be the kinetic energy divided by the temperature of the ground. Okay. Okay, the energy lost is going to be the kinetic energy, which is going to be change in entropy, temperature of the ground. And what are we supposed to show? 52. The unavailable work. Change, and that would be the lowest temperature. Okay, so the temperature of the ground is the lowest temperature, and we are done. Check. All right, so it works in that case. B. A free adiabatic expansion of an ideal gas. Okay, so from equation 20-7, we have the change in entropy is going to be NR natural log volume 1 divided by volume 2. All right, and from equation 19-8, we find that the work done is nRT natural log volume 2 divided by volume 1. That's a 1 in case you're wondering. I know you're wondering if that was a 1 or not. All right. Now, since T1 is equal to T2 in this particular guy, T1 is T2. The energy loss is going to be TL delta S, which is going to be 1/2 T2 MR natural log volume 2 over volume 1, which is equal to the work done. But what we're trying to do is show that the unavailable energy, the energy loss, is TL delta S, which I think we've done that. So we did that right there. C. The conduction of heat, Q, from high temperature to low temperature. All right, so I got some heat being conducted from some high temperature going to some low temperature. All right. So change in entropy is the heat high, temperature low, minus heat high, temperature high. Okay. And the energy loss is going to be TL HL minus QH over HTH which is the carried efficiency of the work, and energy loss is TL delta S. Okay, another one done. Thus ends chapter 20.